So in the last class, we were discussing about properties of determinants. So we'll just quickly review. This last class was last Wednesday on matrices and determinants. So we'll quickly review that and move forward. So we learned in the last class how to evaluate determinant, and how to evaluate determinant about any row or any column. And then we discussed these following properties. If a row or a column has all zeros, then the determinant is 0. If any two adjacent rows or columns are interchanged, then the sign of the determinant changes by -1. Now, if each row or column is multiplied by a new number k, then the determinant value becomes k times the original determinant. So in other words, when you multiply a determinant with a number k, then that number gets multiplied with any one row or one column of the determinant. It is not that, unlike matrices, k gets multiplied with all the elements of the matrix. So determinant of k times a matrix, nth order square matrix, will be k power n times determinant of that square matrix. If any two rows or columns of a matrix are identical, then the determinant becomes 0. If the elements of any two rows or columns are of the same ratio, then the determinant is 0. Just following the previous result. Then, yeah, today's strength is less. So many are missing. 2-day break effect, I think. Then if you have determinant as like this, like a row or a column having two terms, then we can split into two different determinants. Of course, if we have two rows like sum of two terms, then it will split into 4 determinants. This we discussed this. Now next, any determinant, the original determinant, can be written as in this form. Any row can be written as the sum of that particular row elements plus kth multiples, or kth multiple of any other row. So here the second row is transformed to a2 plus k times a1, b2 plus k times b2, c2 plus k times c1, b2 plus k times b1, c2 plus k times c1. So by this, the determinant value does not change. So when you add equimultiples of one row to another row, then the determinant value does not change. Last one, the sum of the products of the elements of a row or column with the cofactors of corresponding elements of another row or column, this will be 0. So this we discussed. Take any row, multiply it with cofactors of any other row and then sum it up. That determinant will be 0. Okay, next we'll move further from here. So properties of determinants continued. So next property, and this is pretty much based on factors theorem. Now if the elements of a square matrix are polynomials, all of them polynomials in X, and the determinant becomes 0 when substituting X equal to A, then X minus A is a factor of the determinant. Now this is a common law for any polynomial, and mind you, determinant is a polynomial. Suppose the elements are polynomials, then the determinant will be a polynomial. So let us say here let f of x be determinant of f1x, g1x, h1x, yeah, then f2x, g2x, and h2x, and so if so now this f, g, and h all are polynomials. Now when you take a determinant, you will get product of three elements. Product of element of three different rows and columns. Each term will be like f1 g2 h3 minus f1 g3 h2. So each term will be having a term, an element of a different row and different column with an appropriate positive or negative sign. So this will also be a polynomial. So if f of a is equal to 0, then x minus a is a factor of f of x. Very simple. This is simply like factors theorem only. There's nothing more to this. It is just factors theorem. This property is simply based on factors theorem of polynomial equation. All right. Next, simple result. Next one. Determinant of A is equal to determinant of A transpose for a square matrix A. Okay. Determinant of A is equal to determinant of A transpose. Next, this is easily understandable. Only rows becomes column, column becomes row. So when you take determinant, you can expand about either row or column. You will get the same thing. Now, determinant of AB, both should be square matrices, okay, of the same order. Then this is same as determinant of A and determinant of B, where A and B are square matrices of the same order. Okay, this can be proved. It is not difficult. We can prove this. Last one.
Sir,
Yes.
sir, like the 10th one, I did not write it little up.
10th or
Once can you
9th?
put that?
9th.
9th one,
Achha,
yeah.
oh,
Yeah.
okay, okay,
Like
okay.
today's first one. Actually,
No,
you
this is
kept
10th
the
only.
numbering wrong.
Yes, this is 10, this is 11, this is 12. Okay, thank you. Take down.
Here only, if f of a that thing.
Done?
Sir, done.
Okay. Then important. Then determinant of a power n is determinant a whole power n. Why? Because LHS is determinant of a into a into a n times. Sorry. And based on the previous result, it will be determinant a into determinant a into determinant a n times. All right. Next. Determinant of a diagonal matrix or comma lower triangular matrix and upper triangular matrix are products product of their diagonal elements. You take any lower triangular, upper triangular, or diagonal matrix, and the product will be product of the diagonals will give you the determinant. Straight away you can do it. So these are properties of determinants. Now we'll do some problems on determinants. These are using these properties. Now like any math, um, like trigonometry has certain rules, and based on that certain rules you need to practice problems. Likewise, for determinants you will have to practice. You'll have to practice how to evaluate the determinant using all these different properties. They're very useful ones. This is like standard what the problems that I'm going to do today. Sorry, this is not properties, these are problems. You'll have to practice the problems on properties of determinants. That is better. Actually, with practice, you will really like how to shorten the solution of a in finding the determinants. So 1a square, these are very standard ones. Show that this determinant is equal to a minus b into b minus c into c minus a. So let us start. See what I do. Now what I do, say I will use the row operations. What is that? I will write R2 as R2 minus R1 because we always can write any row uh, as that row multiplied by k times any other row. All right, either 1, 2, 3, 4. Then the determinant value does not change. Okay, so what we do is R2 we write as R2 minus R1. Simultaneously, we can do so R2 changes. Now don't try to change R3 using the new R2. You can do that also, or simultaneously I will write R3 as R3 minus R1. R1 has not changed, but what I have done, I have written R2 as R2 minus R1, R3 as R3 minus R1. Why? Because, very important, I want to make these two zeros. If I make these two zeros, it will become very easy for me to evaluate the determinant. So because this 1 and 1 are there, I can easily make them zeros. So by this operation, the left hand side becomes now R1 remains as it is.
Sir,
Yes.
it would be easy like if we substitute R2 as R2 as R1 sorry R1 as R1 minus R2, right?
Same. Doesn't make a difference.
Okay.
You cannot do 3 changes simultaneously. There are 3 rows. So you can do 2 changes simultaneously. If there are n rows or n columns, you can make n minus 1 changes simultaneously.
Okay.
So what I did, R2 minus R1. So 1 minus 1, 0. This is b minus a, and this is b square minus a square. B square minus a square. Then this is 1 minus 1, 0, c minus a, and c square minus a square. So now I will use another property. I can pull out a factor from any particular row or column. So from this row, the second row, I can pull out b minus a. So if I pull out b minus a, from the second row, I will pull out b minus a. So I'll get 0, 1, and I'll get b plus a. Correct? Correct? To a determinant, if I multiply by a factor, that factor gets multiplied to a particular row or particular column, not all the rows, all the columns. So I will, the common factor here is b minus a and b minus a into b plus a. So I pull out b minus a. So I get 0, 1, b minus a, b plus a. Then similarly from the last row, I can pull c minus a outside. Then this will be 0, 1, c plus a. Now it becomes very easy. You see here 1, 0, 0. So expanding. Now expanding the determinant about the first column. Okay, we get b minus a into c minus a. Now first column you get 1 times b2 c3 minus b3 c2. Okay, so 1 into c plus a minus of 1 into c plus a minus of 1 into b plus a. The whole multiplied with 1. All right, 1 times 1 into c plus a minus 1 into b plus a. So you get b minus a into c minus a into a cancel, you get c minus b. So write this as a minus b with a minus sign. And then second one, b minus c with a minus sign. So two minus signs become positive, plus 1. And then write c minus a as it is. So a minus b into b minus c into c minus a. Okay. Got it? How to do? Next. Second problem. Show that determinant of 1 a square a cube 1 b square b cube 1 c square c cube is equal to a minus b into b minus c into c minus a times ab plus bc plus ca. Same procedure. So you participate with me. You tell me the steps.
Sir, R1 as R1 minus R2.
Better to keep the first one as it is because it is 1. Better to do R2 as R2 minus R1.
Sir, but if we do R1 as R1 minus R2, we can get directly, right? A minus B and B minus C.
Okay, second step. That also you can do. Okay, I'll do what you're saying. R1 as R1 minus R2 and R2 as R2 minus R3. We can do this. Okay, so left hand side becomes 0, a square minus b square and a cube minus b cube. Then you get 0, b square minus c square into b cube minus c cube. And last one, 1 c square c cube. Okay, this also you can do, or you can do, as I said, keep R1 as it is and do the other two. Next, this I can write as 0, a minus b into a plus b. Then next one will be a minus b into a square plus ab plus b square. This is b minus c into b plus c. Then b cube minus c cube is b minus c into b square plus bc plus c square. Then you have 1 c square c cube. So now how will you expand? Expand about the first column.
Sir, we can take A minus B common.
So
from
you
R1.
can take a minus b common and b minus c common. You will simplify it to 0, 0, 1, a plus b into a square plus ab plus b square, b plus c into b square plus bc plus c square, and c square into c cube. So now let us do this. When you expand about the first column, this is plus sign, minus sign, plus sign for cofactor. So cofactor will be 1 time, determinant will be, this is 0 times plus 0 times, 0 times minus 0 times any other term, plus 1 time, yeah, this one, a plus b into a square plus ab plus, sorry, a plus b into b square plus bc plus c square. A plus b into b square plus bc plus c square minus b plus c into a square plus ab plus b square. Okay. So you have a minus b into b minus c. Now we need to simplify. We need to simplify this one. So let us do. You get a lot of terms. ab square plus abc plus ac square plus b cube plus b square c plus bc square. All right, minus of, all terms will be minus, b a square b a square, okay, then plus minus ab square minus ab square minus b cube minus ca square minus abc minus cb square. So many terms cancel. AB square cancels AB square. ABC cancels minus ABC. AC square, no. Plus B cube minus B cube. And then B square C and BC square. So B square C and B square C cancels. Then we are left with AC square plus BC square minus BA square minus C A square. Okay. Let us do this calculation. A minus B into B minus C times. Let us see this. AC square minus CA square. So if you take AC common, you will get C minus A. Then take the next term. BC square minus BA square. So plus B times, you get C square minus A square. You can simplify this, write this as A minus B into B minus C. C minus A you can take common. Then you'll get AC times 1 plus B times C plus A. Okay, so you get A minus B times B minus C into C minus A times of AC plus BC plus AB. So you get AB plus BC plus CA. This is your right hand side. So what did we do? It is all algebraic simplifications only. First, you do row operations and then pull out common factors and then just evaluate the determinant and simplify. Just that you have to have little patience and perseverance to solve the problem. All right, next question. He has given complex numbers also. How will that be? All right, some exercise problem. So one problem is there on cube roots of complex number, but details of complex numbers you will learn later. See, if 1 omega and omega square are cube roots of unity, then find the value of 1 omega omega square omega omega square 1 and omega square 1 omega. Now here you have properties. You will not get this problem just like that. Properties of 1 omega and omega square. See, basically, this is.
Sir, is the answer 0?
Yeah, answer is 0. Basically, these are roots of x cube minus 1 equal to 0 because they are cube roots of unity. So x cube minus 1 is 0. You factorize this as x minus 1 into x square plus x plus 1 equal to 0. So you get 3 solutions. The second root is minus b plus or minus root of b square minus 4ac. B square is 1 minus 4, that is 3i by 2. So it has certain properties. 1 cube is 1, omega cube is 1, omega power 6 is 1. They're all 1. Also, you can see that 1 plus omega square equal to 0. So solution of one omega square how to do? I'll do row operation like this. See, I will transform row 1 as row 1 plus row 2. Then after that, next step, I can the transformed row 1, I can do the transformed row 1 plus row 3. That means I can do this operation, row 1 as row 1 plus row 2 plus row 3. When I do that way, I get one plus omega square, omega square plus 1, same, omega square plus 1 plus omega. All three are zeros. Now, all elements of a particular row or column is 0. Then what happens? It becomes 0. Okay, that's how we do that. Okay, evaluate determinant of A, B, C, B, C, A, C, A, B.
Sir, so there's only one property for the previous question.
Yes,
1 plus, okay, sir.
because that's 0. Because we have not done complex numbers, this property is not known. That's why I've gave that property.
Like any other property, if there is like different kind of question involving the same variable.
Yeah, maybe you can get, but this is a standard property for this is a very, very important property for complex numbers, cube roots of unity.
Okay, sir.
Okay, it comes from this. Add these three, you will get 0, the cube roots. Okay, evaluate this. See, this is a determinant with cyclic coefficients or cyclic elements. ABC, BCA, CAB. So how do we do? Look at this, how to simplify in an easy manner. One method is directly evaluate about first row or first column and solve. Okay, that is a valid method. Sometimes instead of doing the operations, evaluating the matrix or the determinant directly will be useful. Some cases. In some cases, you may have to use the properties. So let us do this both ways. Okay, I will do method 1. I'll do method 1 direct. Yeah.
Sir, is the answer minus a cube minus b cube minus c cube plus 3abc?
Yes, that's right. Now method 1, I'll write this determinant as delta. ABC, BCA, CAB. This is A times, or expand about, the first column, let us say, A times BC minus A square. A times BC minus A square. Minus of, now minus of B. Omit the first column and the second row. Then you will get B square minus AC plus C times AB minus C square. So I get ABC minus A square minus, A cube. This is minus B cube plus ABC plus ABC minus C cube. So we get 3ABC. Very important result, this one. Standard result, you can remember also. Now I will do the same thing in a different way, and let us see how the answer varies. But upon simplification, you will see that the answers are the same. I have this A, B, C, B, C, A, C, A, B. ABC, BCA, CAB. Now for this, what I do, I will write column 1 as column 1 plus column 2 plus column 3. Okay, this is column operation. Just like you can do row operation, you can do column operation. Column 1 I write as column 1 plus column 2 plus column 3. What happens by this? By this, I get A plus B plus C, B plus C plus A, which is A plus B plus C, and C plus A plus B, which is A plus B plus C. And then I have BC, CA, AB. Now I can take the common factor out from any particular column or any particular row. So common factor is there in the column. All right. Now, next I will do row operation to make these two zeros. So I will do row 2 as row 2 minus row 1 and row 3 as row 3 minus row 1, or row 2 also you can do row 3 minus row 2. So I get A plus B plus C times 1 B C. Next 1 minus 0 is 0. Then C minus B is this, and then it is A minus C. 0, C minus B, and A minus C. And then this is 1 minus 1, 0, A minus B, and B minus C. So now we can expand about the first column. It becomes easy, one term only, expansion. It is 1 times C minus B into B minus C, okay, minus minus A minus C into A minus B. Let us see what we get from this. We get A plus B plus C times, this is minus of B minus C the whole square. So I'll get 2BC minus C square minus B square minus C square, that is the first term, minus of this is A square okay, this is A square minus AB minus AC plus BC. So what do you get? A plus B plus C, observe this, 2BC minus BC is 1BC. Then this is plus AB plus CA. So I get AB plus BC plus CA minus A square minus B square minus C square. Okay, so this is the answer. Now if you compare the two answers, both are identical. Actually 3ABC minus of A cube plus B cube plus C cube is equal to this one, A plus B plus C times AB plus BC plus CA minus A square minus B square minus C square. Actually the identity is this, it's a standard identity, standard algebraic identity. Is A cube plus B cube plus C cube minus 3ABC is A plus B plus C times A square plus B square plus C square minus AB minus BC minus CA. This is a very well-known identity. In straight lines, we have questions like this. For the three lines, AX plus BY plus C equal to 0, BX plus CY plus A equal to 0, and CX plus AY plus B equal to 0, to be concurrent, what is the condition? The determinant should be 0. So there you get this condition. Either A cube plus B cube plus C cube minus 3ABC is 0, or A plus B plus C is 0. There is a version for this. This is also equal to, now you observe this, the way I write this, very important result. When you expand this, you can see this. See, a into a square, a cube, b into b square, b cube, c into c square, c cube. So a cube plus b cube plus c cube term comes. Now next, a b square. All right. Now you multiply b with minus ab, you will get minus ab square. So ab square and minus ab square cancel. Then you get a minus bc, that is minus abc, you leave it as it is. Then you get minus ca square minus c a square, and then you have plus ca square, that gets cancelled. Like that, if you expand and see, all terms gets cancelled. You will get a cube plus b cube plus c cube minus 3abc. That's what you will get. Okay. Now this is a plus b plus c times. This I can write further as half of say this, a minus b the whole square plus b minus c the whole square plus c minus a the whole square. See this? See this expression. A minus b the whole square will be a square plus b square minus 2abc. B square plus c square minus 2bc. C square plus a square minus 2ca. Now this c square and this c square becomes 2c square. A square plus a square 2a square. B square plus b square 2b square. So you get 2a square plus 2b square plus 2c square minus 2ab minus 2bc minus 2ca. Just multiply this by 2. You get this expression. So that's why this expression is half of this. Okay, these two are very, very important expressions. You have to memorize. It will be very handy. Okay. So this is one. Last problem for today. Find the determinant of 1 square plus 2 square 3 square 2 square 3 square 4 square 3 square 4 square 5 square. We should know that the difference of the squares of natural numbers, they form an AP. Very, very important result. Okay. 2 square minus 1 square. Okay, I'll write here note. Side note. 2 square minus 1 square is 3. 3 square minus 2 square is 9 minus 4, 5. Then 4 square minus 3 square, 16 minus 9, 7. Then 5 square minus 4 square, 9. Then 6 square minus 5 square, 11. So like this sequence it is. All right. The difference between these two is 2. Always the difference is 2. So they form an AP 3, 5, 7 like that. So that property we'll have to use. So let this be delta. So let us do row 2 as row 2 minus row 1 and row 3 as row 3 minus row 2, the old row 2, not the new row 2. Okay. So we get, first you do row 3, so that, and then do row 2. So row 3 is 3 square minus 2 square, 4 square minus 3 square, 5 square minus 4 square. Row 2, 2 square minus 1 square, 3 square minus 2 square, 4 square minus 3 square. Then you have 1 square, 2 square, 3 square. So this becomes 1 square, 2 square, 3 square. This is 3, 5, 7. And then you have 5, 7, 9. Now what do you do? Now what do you do? Again, you can
We can expand directly, right, sir?
expand directly, or again you can simplify. Again you can do one minus the other. That also you can do. If you want to reduce, it will not make a
Column
big
wise,
difference. Column row wise you do R3 as R3 minus R2. So you get 1 square, 2 square, 3 square, 3, 5, 7, 2, 2, 2. So then take 2 outside, you get 1 square, 2 square, 3 square, 3, 5, 7, 1, 1, 1. Okay, now you can expand directly, that is better, about the last column. 1 times, omit the row and the column containing the first element. Then you have 7 4s 28 minus 5 9s 45 minus, then this term, omit the row and the column, then you have 1 square into 7 minus 3 cube, 9 3s 27, plus 1 times 5 minus 3 into 4, 12. So twice of this is 17. This is plus 20. This is minus 7. Okay, so you get minus 24 minus 4, you get minus 8 as the result. All right, so I'll stop here. Few more problems on determinants tomorrow, and we'll do adjoint and inverse of a matrix. See, I have all the assignments ready with me in this Word form, but when I have to upload into Moodle, I have to convert into a mathematical equation in Moodle form. So that is consuming a lot of time, and I take help of someone to do it, and he was very busy in the last 3 days, so I couldn't put that assignment. Trigonometry assignments, I was working very fast on it. So I will put on within 1 or 2 days. I'll put on the matrices and determinants assignment.
Sir, what about matrices quiz?
That's what I'm saying. Quiz means assignment only.
Okay.
I gave assign. Okay.
Thank you, sir.
All right. Who all are missing today?
Sir,
Who all are missing? Yeah, 1 second. Vishnu Das is missing. Yes, Prisha?
sir, I'm now turning two questions. Sir, is that fine if you can discuss it right now?
Yes, we can.